Hello, how are you doing? Okay, so I hope you're doing good. Make sure we download the notes and the assignment for today. We'll get started in a couple minutes. Let me get at that. So today we're going to go over chapter 6 and do a little bit of explanation and then a little bit of coding. So let's take a look at chapter 6 or unit 6 notes. And then we are going to look at your assignment as well. And for the lab this week, we're going to do sequence. So let's download your assignment. Okay, I'll go ahead and get started. So for today, we're going to take a look at chapter 6. Let me zoom in real quick. And in this chapter, we're going to focus on how to solve the problem. We started working on the lab last week, and we started to see how we can take whatever's that's asked in the question and be able to put that into programming. And I think many of you have done this in your other courses and your projects. So we're gonna break it down to the subtasks today and how we would be able to apply that to assembly programming. So to really define programming, it's just a way that we would be able to write or create computer programs. And what we want to do with these programs is to really solve the bigger problem. So for example, if I own a company, I want to be able to create a program to help my customer manage their purchases or their order. I could also create program for my financial needs to have financial tracking. So we started to see a lot of the programming is really to help alleviate or reduce the problem. Now you also see a lot of this in the current trend in the cloud, where we don't really construct a complete program anymore. You can write functions to be able to execute the task instead of the entire program. But in this class, it talks about programming as methodologies to be able to perform a desired function. So if we take a look at problem solving, it's just a way that we would take the overall problem or the description of it, and we would break it down into smaller pieces so that way we can address the main problem by looking at how we can have a manageable units of the task to be able to build out our program. So this process is called systematic decomposition. It's a way that we would take a larger task and break it down into the smaller ones. And you saw this in the lab last week when we said that we are going to write a program that's going to take a number input and output a day of the week. So that means that we can take that and then be able to look at what kind of tasks that's going to be involved. Are we going to be loading and storing Do we need any kind of memory addresses? So in our case, we need to really make sure that it's seen in digestible units, so that way we can bring it down to the machine level, so the low level programming. So make sure that we understand the definition of systematic decomposition. This is going to show up on your exam or quiz. And it's a way that we would break down or decompose the main task to subtasks, and even smaller than that. So you would make it down to the machine instruction level, which is what we're working with. And this is where we would see the normal instructions that can be used in assembly programming. So in answering the first question, it asks you, how can you use problem-solving techniques in assembly programming? Describe the process of solving a problem using programming. And you can take this and apply it to other languages as well. Doesn't have to be assembly. But the first step is to really derive a problem statement from the question. So if you are asked in the question to solve a certain problem, you want to take the portion of the problem statement and you want to look at it closely. Then part B, the next step is to convert the problem statement into step-by-step description or subtask. And this is simply, when you learn programming, they normally go through this process to teach you how to pseudocode, right? We take the problem statement and we're going to break it down to a procedure, which is a step-by-step description that includes the subtasks to solve the problem. And you also see this in math. In programming, we need to correlate 3 basic constructs. Sequential, which is top-down, right? Conditional, which is a way that we can move from one part of our code to a different part of our code, not necessarily the next. And iterative, and this is what we use for repetitions, or it could be for looping. So all of these components or constructs, that's going to make up your machine instructions. So again, derive the problem from the question. We want to take the problem statement and we want to break it down into step-by-step subtasks. This is what we call procedures, and eventually build it out as an algorithm. And then we want to correlate the basic construct with sequential, conditional, and iteration. Any question? So coming back here, right, I did put down some of the information that you can see with systematic decomposition. And this is what we see with the step. So when you're using the step, you want to refine the step. And so after you have laid out step-by-step tasks or subtasks, you would then convert that into an algorithm that could be in LC3 machine instructions for this class, or that could be in a programming language for your other classes. And so when we talk about the sequential and conditional and iterative, we want to think about how we can go from one task to the next. That's sequential. So if my program consisting of 10 subtasks, right, I need to go from the first through the 10th. Whereas if we applied the conditional, right, that can be where it would check if it is true, it's going to execute the first subtask. If it is false, then it's going to execute the second subtask. So when we do if-else statement, or when we use conditional statement, this is what you would see. And then for iteration, we would have what we see as a loop. It's going to continue to execute the subtask as long as it is true or it met the test condition. If the test condition is false, then it's going to exit. So an example that you see in the text or in the PowerPoint, we can have a program that counts character. And we want to print out the number of times that certain character in the string occurs. Or it could be in a file. So if we're doing character count, what we have to see is we have to look at how we're going to achieve this by breaking it down into the smaller processes. For example, getting an input from the keyboard, right? And on the machine level, we have to think about, oh, well, an input is a character, a text, right? And it's going to come in as a value. So we have to add in the ASCII conversion, right? We got to move it, ASCII convert, and so on. So as you're getting used to LC3, you're going to see some of that. After I have an input, I need to copy it to another register from register 0. Then I'm going to go through the process of adding the decimal 48 or subtracting the decimal 48, and then to ASCII convert and then handle the numerical value from there. Before I print it on screen, before I output, right, I have to convert it back. So there are subtasks that we would see in order to handle. But can I implement a loop? So what we can see is we can apply a condition by using test character. So if I'm asked to count a certain letter, for example, if I'm asking to count the letter C in the file, I would ask the users to input the test character, and I would apply the conditional statement. If the character is C, right, if that's true, it's going to count, and we can have it increment. If it is false, then it's going to exit, and it might display something. It might display that the test character is not found. For the loop, for the iteration, we can have something like a do while. We would have it do over and over as long as the condition is tested true. So in this case, it's going to check each element of the file for that specific character. And if it finds it, right, it's going to count it. If it's not, then it's going to notify us. So in any kind of problem for programming, you have to think of those 3 constructs, okay? Sequential, conditional, and iteration. And so when you get an interview question, if they ask you to solve for something, you have to think about, how do I approach writing this program? Should I implement conditions, iterations, or is it just going to be sequential, one task to the next? So, and you don't have to put all of this down, right? I copy and paste this from the notes to kind of show you. On the last step for E after D, we want to also mention that you have to decide on how you would approach the problem, right? Because as you've seen in the last lab, we can have many ways to solve the same problem. You're going to have to make a decision, and your decision should be based on efficiency. And then once you decide on how you would implement the algorithm, then you would document it. And so we always consider the three basic constructs when we are approaching a programming problem, whether it's for analysis or to create a web program or to do a robotic program. Now, in the case that if your program doesn't work, right, we have to go through the debugging process. And so I'm just going to show number 2 before we get into it. But as you've seen this in other programming courses and experience, right, I always tell you that if you see an error, look at that error and it will tell you where that is. And the first thing that you should check for is how you type your code, which is syntax. So syntax is just a rule on how we would be able to program in specific language, like how we use period, comma, question marks in plain English or in our speaking language. So after we look at the syntax, and if that's not that type of error that we come across, then the next step is you need to check for logic error. And in my opinion, A and B are much easier sometimes than combing through the data. But in the simulator, we can use the tools. So if you're programming in C++, Java, or other languages, right, you can use the element, the feature in your IDE to really look at. And a lot of the IDE is really good at pointing out, right, it has good debugging feature, okay, so, or a debugging engine. So in LC3 for this class, we want to use the simulator to be able to help us detect or fix the error. And then for C, we want to check for data error. Your program could work, right? And the reason why a lot of the times we store out to a certain memory location is this is where we would be able to check our result, right? When you fill a certain addresses, you can set the value and be able to use those values to compute and then go look at where your result would end up. At that address, you can verify. Because ultimately, everything breaks down to binary, and we can use binary or hexadecimal value to be able to verify. So when your program doesn't work, these are the 3 primary tasks that you need to really work on, is to check syntax, logic error, and data error. Any question? All right. So the question 1, this is where I got most of your answer, right? But it also is in the specific detail. Okay. And the more questions or things that you highlight that's related to the problem statement, it's going to help you identify how you're going to be able to address your problem statement. Okay. And so, and I pulled this from your PowerPoint. So this is where you can see a little bit more on the graphic side. So on our simulator, what you would see is you would see how it would use certain kind of flag, or like for NZP when we're doing conditional branching, right? This is when a couple weeks ago we spent a lot of time looking at the binary equivalent of that instruction. So once we do that, we can see how that would be in binary. So you can go in and visually check it. You can step over, step through. Okay. Now, sometimes you are going to have multiple iteration of your program, right? Usually you do. And so when you solve a problem, the first solution is not always the best, of course. And like I said before, sometimes we take a look at it again. How can we refine that particular solution? Can we implement other things this is why sometime on the lab, I ask you, how can you improve this program? So we have to think of ways to really refine the subtask to really build out the solution for the main task. And this is how you see version control being used, right? So as you can see from going from the first solution from start to stop of the program, and this is like a sequential program, I can possibly implement something that would be like a condition or an iteration. So in this case, we are going to implement a loop. Now, a loop is still pretty sequential. I think as it's going to go from start to end, right? And now we are able to capitalize on a lot of the hardware resources to be able to see how we can concurrently do stuff on the higher level programming like Python. But as you can see, going from a top-down program, going from one task to the next task to the next task, I can do it 10 times, or I can create a loop that loops it 10 times, which is a lot more automated compared to if we are just going to go top-down. Okay. And so debug information for number 2 is here. So I see a lot of the challenges with some of the students that just started beginning to program. It's harder to find where the error is if you're not familiar with it. But once you identify it and it comes up again, it's a lot easier to track. So some of the debugging technique is if you are tracing through your program, it is really important that you're looking at the sequence of instructions that's executed. So I get some email questions throughout the week and on the weekend asking like, why is it doing this on this line? Why is it showing this result? And I normally tell the student, what are you doing the step before, right? You have to really look at the sequence of the instructions, the prior steps that is being executed to be able to derive where you're at in your line of code. And in LC3 in assembly, it's very important that you're tracking your results and you're tracking where things are stored, right? I had a question before about, can I just use any of the registers? Sure, you can, but it's a lot easier if we're tracking what numerical value at which register at that point. Okay, so at the end, we want to look at whether the result is going to be accurate if we're able to achieve that. Because if you're not tracking your resources and your results, what's going to happen is you're not going to be able to achieve the accurate final result. And we need to really compare the result with each of the instructions. Looking at the addresses, looking at the location where data is stored and how it's full, and what is your expected results. So if I ended up with something that's 1 off or 2 off in value, then I need to trace back and see where is that added incorrectly, right? That's a way that I can fix it, okay? So in LC3, I put down the values in memory and registers are important, how it's displayed and how it's stored. and then how your sequence in your program, how it's executing instructions. And it could also be that sometime we put in the incorrect instructions. We meant to do add instead of and or sometime if it's overriding a certain register and we're getting a different value. Okay. And then what you can do is you can comment certain things out to test your program so that, or you can put a halt where it's going to stop that specific execution task. And so you can see, because the program counter track all of that. So we can, and in your simulator, you can put a little stop mark to be able to track it. Okay, so here is the little buttons that you can use. And then as highlighted earlier, I talk about some of the syntax issue. That's very common, how you type, logic issues, and data errors. So for the data side, we have to see how the data is input. If you fill how you initialize the data instead of, having the manual input like in and out, then is that different than what you expected? Okay. And then you can also set the value at a certain address location. All right. And on the logic side, we also look at what's legal, what's wrong, how certain logic operators are used, or how our algorithm logic is. Okay. Sometime if it's an illegal operations, that's going to create logical error. Okay. So let's go to the next part. We are defining systematic decomposition. This is how we can decompose each of the tasks into the smaller subtasks, or even the smaller task than the subtask. So you need to break it down to where it is at the machine level. So if you think of everything in higher programming language, like, oh yeah, I would start with defining a variable, right? And you have to take that task and say, okay, what is defining a variable equivalent to in machine instructions? I would first need to load a label to a register. And I would fill that label with a memory address. And then if I initialize that variable with a certain value, then the loaded register is then added with the value. So you have to think of how you would break down a task into the subtask and then machine instruction level. And we talked about how you should debug your program, examine the sequence of your instructions, keep track of your results that's being produced. And I don't expect you to comment every line in your program for your project. That's a lot, right? I'm not going to ask you to do that. But if it helps you, you need to periodically comment so that way you know and you can track. Okay. So far I've been commenting every line to kind of help you follow along in the code. But down the line, right, I'm expecting you to comment some part of your code so that way either for you, right, or for the person who's reviewing your code. In this case, it will be me. But it's always good to add comments for other developer to go in and kind of take a look at the essential area of your program. So let's take a look at some of the issues with how we type our code, right? When you incorrectly type a certain instruction, like in this case, load, this is not acceptable in LC3. maybe other language it might, but for LC3, we do LD, LDI, LEA, or LDR. So automatically we know that this is a syntax error because it's typed wrong. For B, the output of the program yields a negative value. So we see that X plus Y is in an absolute symbols right here. So that needs to be greater than 0. Now we learn how to do absolute value of a variable plus another variable. We did this about 2 laps back, right? You would check for values that's greater than 0. But in some case, if you have a different flag in there when you branch, that could generate a logical error. So it's still going to output some result. It will be the incorrect result. So that will be your logical error. Because it's illegal to have negative value for absolute. Okay. And then for C, data input value is less than the given expected test result in the problem statement. So your expected value is different than what you got. That's a data error. So I would look at how I initialized the data or how I handled the data through operations. And so I would have to trace back on why my result is off. Any question? Okay, so this is pretty basic. We've seen this before, probably, okay, in other classes. All right, let's go through number 6 together. So what I did was I gave you problem statements, and the whole point in this is to kind of build out pieces of your program in LC3. I know some of you can just whip through this because you know, right? And then some of us are still trying to get used to LC3. So this is the whole point in this type of exercise. All right, so given the below problem statements, create problem statement questions or, and then convert the problem statement into an algorithm using stepwise refinement, and then convert the algorithm into an LC3 program. So I'll add to this. So you're given A, create the assembly program that contains the criteria. X is set at the location hex 3400. So when you see this in the lab, you would know that, right? So what we should ask is hex 3400 a memory address? Okay. And we can also ask that, is this location being used for to set value? And so if we answer yes and yes here, right, then we know that we would possibly fill X at 3400. We would then need to declare the label X. So what I did was I look at the problem statement. I take that here and I put it into a question. So I can ask myself, is this correct? Right? And then I would refine it into the step. Okay. And then I convert it into LC3. So in red, that's what you see as LC3. So for the X label, I would do a dot fill hex 3400. And we can do the same thing for the next one for Y, right? Is X3401 a memory address? Is this location being used, or I would say a is address the second input? And input doesn't have to be through the console, right? It could be a data input from an address location. Okay. So if we initialize the data and tie it to a location, Y is simply a name that we give this address. Okay. So if this is the case, then we would fill Y at hex 3401. We would declare the label Y. And so for our code in LC3, we would say Y dot fill hex 3401. So that makes this a second input and X is the first input. It could also be that these are just location where it stores result. We don't know how the program would be, right? We simply see the only statement and then we would convert it. I shouldn't say second input, a input, an input. All right, so once we have the location for X and Y, the next statement is that it tells us that X is 3. So what we need to do is we are going to say so we would say X is initialized as integer or decimal 3. So our step for the next part is to load X label to the register, right? That's step 1. And then for step 2, what we're going to do is we are going to add the decimal 3 to the loaded register. And so once you see it like this, you're like, oh, I just need to load X to a register and then add 3 to it. Then I can do, and you can do LD here, okay? I just use LDI, so I would do LDI R1X, load label X to register 1, and then I add register 1 with 3. Now, some of you might want to clear the register and then load it. You can do that too, right? So if we do a clear register, then you simply add another line. So we would do an and R3 with a 0. And put decimal 0. And that is an optional step for you. You don't have to add it, but you can, right? So I clear the register here. I'm sorry, R1. I was thinking R3 for some reason. R1. So I clear register 1, and then I load it with label X, and then I add the 3 to it. So R1 is 3, and that is X. Okay, so later lab, we're going to do multiplication. So I'm previewing you right here to some of the things we're going to do later. So for the next step, it tells us to take y and we're going to multiply x 2 times. So y is 2x. And we know that multiplication is a way that we add things multiple times. So we would take x plus x. And if I do 4x, then I just do x plus x plus x plus x, right? And so here is where you can consider, well, if it's multiplication, I could loop it, right? If I'm keep adding it multiple times. Or I can just sequentially go through and then add it. So some of the things that you should consider here is we know that multiplication is addition in multiple times. And possibly we can implement loop, which is iteration. But in our case, it's pretty simple. It's 2x, so x plus x. So if we break this down to our steps, we know that number 1, we're going to load y label to the register. Then we're going to copy x register to the y register. Why do I need to do that? Because I already have the x value, right? I just need to copy that value to the register where my y label is. So it's the same. Then I'm going to add it for multiplication. And then since I load at the beginning, I'm going to store that to a register, to the y label, so I could see the result or check it. Now, if I have 10x here, what I can do is I just need to copy x to the y register, right? And then to be able to increment, I can send it through a loop. So when it's doing that, right, I'm just going to keep adding it multiple times for this part. So for my code, I would start with loading the y to a different register. So in this case, I'm using R2. And again, you can use LD and ST. I'm just gonna use LDI because I used it in the last one. So you are going to load y to register 2. And then what I'm going to do is I'm going to copy the value in register 1, which is 3 from the previous step, or x. So x is 3 and it's in register 1. I'm going to copy it to register 2. So here is where I have y is equal to x. Then after that, I'm going to take it and add it to its cell. So I would have 2x at register 2. Now, another way that you can see this is instead of copying, right, I can represent the 2x at register 2. Okay, so I can say R2, add R2, R1, R1. That can be done too. Okay, So this is one way to solve it. Another way is you can do it this way, or you can do it add R2, R1, R1, which most of you probably see. X plus X, which is 6. So we can do it. And so you can see that you can solve it multiple ways. What if I just don't want to copy? What if I just want to say, add R2, R1, R1. It's still going to be equal to 6. If I do a copy here, I have an extra step, right? I have the X is equal to Y, and then I add it to itself again. So it is going to be 6 as well. Okay, so there, as you can see here, and then I would go back and I would refine my step here. Well, I tell myself, well, why do I need to copy if I can just do this? It's still going to be 2x at Y location, or the register that holds Y. Or I can do it this way after I copy it. So it's really how you see what that would, which register would represent what, and how you loaded the register and what value. So any of these are going to be correct. So originally I had it this way. We can also copy and do it this way, or you can just simply take X, add it with X, which is 2X, and then put it on Y. Okay. Any question? Okay, so for the last part now, what we're going to do is we are going to remember that this is one of the things that we need to address, right? Because once it's in register 2, it's not going to stay there. We have to store it out so we can see. So we want to be able to store. So I put that on the next step here. Display on console requires, so that means that we need to bring value to register 0. So this is the step. Okay. Sorry, let's do that again. So store values from register to Y location. Then what we're going to do is we are going to copy value from current register to R0, because R0 is where it's going to pull for output. Then what we're going to do is we are going to use directive out to output, or puts. And I want to verify. So whatever that I put on console, it should also, in transition, it should also be at the location for Y. Okay. So that means that, you know, how I store it out to Y here, I need to fill Y. And we already filled Y earlier at 3,400, so we can check it also there. Okay. Any question? So in my LC3 code, I have STIR2Y. So because I want to show that Y is 2x, so at the location Y, we should see the value for 2x. And then I also want to copy, right? I actually could do this first. Hold on one second. I should copy it first before I store it out. When you copy it, just duplicate the value and it puts it on the register 0, and we need to bring it there so we can output. And then I can store it out to the Y label where I can see it at the address of the value. You always want to put it to a permanent location for the write, because if you rely on register, it doesn't retain value too long. So it's only meant for transient. So what you want is you want to be able to put it to an address, and then I can do a put. Any question?
Yeah, how come it's not 0 at the copy part?
Oh, I'm sorry. Yeah, thank you for catching that. That's right. There you go. I don't know. I forgot. I think I put R2 by accident and then I didn't even see it. Thank you. That's right. Well, at least you're understanding. Let's
Could
put
you
this.
repeat one more time why we have to copy?
Yeah, because register 0 is in charge of input and output. No other register does. So I have Y as a result in register 2, and I need to bring it to register 0 so it can output. If I don't do that, it's not going to be able to output. No other register besides register 0 can output. So whatever register you're using, you have to copy it to register 0 to output on console. Okay. And then I still store it to Y address because it's a permanent location where your results should go. And then so in C++, we at this part we would say cout, right, from a variable. And then, but in that process, it's already storing the value for your variable in a location. The compiler does that before it actually cout. So, you know, whether you write it before or after, it's still the same, because I think it's still achieving. We have it at an address and then we put it onto register 0 so we can output.
But we need to store the value before we output, right?
Yeah, you should. This is just a practice. I really think that you need to put it. Otherwise, you know, eventually it's going to go away. If that value is important for your program, yeah, you have to store it. In some cases, when we use it temporarily, we don't need it, right? But most of the time, yeah, we store it out for the result. we're gonna see later that we're gonna do return from a function. So after it uses register 7 for the return. So it puts the address of the return value on register 7, and then it flushes it out. So as you know, when you do return from a function after the function is called, right? It just gives that space back to your OS. So we're going to talk a little bit about that, how that works, but at least you don't have to write the sub process for the return. Okay. But yes, store the value. Now, because this is really good for us to manually check, right? What if, I can set X as a certain value, and then I just compute and see and look at the Y address. And so I should be able to see double X, and I should see it on console. Sometime we don't output it on console, then you don't need to copy. All right, let's take a look at B. So for B, it says create the assembly program that contains the following criteria. So here are your problem statement. This is what you would see with our lab, right? X and Y and Z are set at location 3100 respectively. So we want to kind of sequentially manage this because you're going to track them. So I can say X at 3100, Y at 3101, and Z at 3102, right? So we can say the step for this would be, let me move this down real quick. We should fill labels X, Y, and Z starting at location 3100 and subsequently. And it's good to break it down like this because it's going to help you with your documentation down the line too. So it's always good to kind of write out what your procedures would be, which is what you also see in pseudocode for most part. So I would do a fill. So X dot fill 3100, 3101, and 3102. Then for the second one, the second bullet, it tells you that X minus Y plus Z is 10. And you can solve it with the algebraic way, right? If you take a look at, if you want to say Z is 10 minus X plus Y. So it really depends on how you see this problem. Okay, so I put that will be the option. Okay, so let's break it down to the step. So what we need is we need to load labels X, Y, and Z to register. Then we're going to operate. And here is where you break it down to the sub piece. So if you're looking at it this way, okay, you need to, once you load the label, you need to operate, moving from one variable to the next. Operate subtraction and addition with registers that I should say loaded register. And then what we can do is we can also initialize value, which is 10, right? And if we solve it this way, right, we just need to check against it. So for comparison or operation. And if we do it this way, we gotta bring 10 into a register and then do the subtraction and the addition. And then lastly, we need to store it out. Result from register to address, subsequent to labels. And then you can check. So I think last time when I did this with the last year class, I chose to use this way. So I'm going to walk you through that, and then maybe if we have time, we'll talk about this side. It should be the same. So the way that I look at this equation is if I subtract x and y, x minus y on both sides, I will get z to itself. It's better that I deal with one variable is equal to this. I'm still gonna do the comparison, right? Because I got a handle on how it's gonna compare between z and whatever is here. Okay. But the point is you're gonna go from step to step. So we're gonna load first x to register 1. That's gonna be one label to one register. We're gonna load y to register 2 and z to register 3. So we got 3 of these. Now we want to, so I'm gonna highlight this. This is what I did. Okay, so this equation right here on the right, which is just algebraically solved from the left. So what we're gonna do is I'm going to take this piece, right? And the way I look at it, it's like this. So I'm gonna make sure I operate x plus y first. So what I did was I used register 4 to store the result of x plus y. So x is in register 1 and y is in register 2. Sorry. Let's do that way. Okay, just disregard the lot. I'm gonna code with you now. So right now what we're gonna do is we're gonna handle the 2 complement. So it's gonna be minus. Actually, that's not right. So what we're gonna do is we have x plus y here. Not x. R1, R1. And this is 1's complement of x. And then we're gonna do add R1, R1 with a 1. And here is where we do 2's complement of x, which is R1 is negative x. Right? So at this point, I have a negative x. And then I decided that I want to do negative x plus y is going to be at register 4. Right? And so now what I'm going to do is I got to bring 10 in. 10 would fit onto our, you can do a decimal 10 or you can do a hex A, same. So what I can do is I can do an add R4, R4, and then a decimal 10 or a hex A. Let's do a decimal 10. R4 is equal to negative x plus y plus 10. Or the same as 10 minus x plus y. And at this point, what I can do is I can store this out, right? To z. So I don't really need this actually. See out R4 to z. And then as we have the z fill here, I would be able to check if I input x and y. Okay. So you loaded x and y for your variable right here, right? And then I operate the negative x here. So negative x plus y. And then I combine it. So I have this. And then I added the 10. So that becomes 10 subtract x plus y. After that, I just store it out to z. So that's the way I look at it. If you look at it this way, you have to do the comparison. So you load the labels like what I had before, and then you would, once you have your label, then you gotta do subtract 10. You gotta bring 10 on the other side, and then you branch it for 0. So that's another way to solve it. And I can code that pretty quickly too if you want. Well, we have time. Okay, so this is one way. Another way is option 2. We're gonna do LDI R1 X, right? We load X, LDI R2 Y, and this is the one that you saw I had earlier. We're gonna do an LDI R3, it's a Z. So what I'm doing here is I'm trying to get this like this. And I need to subtract x just like before. So once I load the labels, I'm going to go ahead and do the 2's complement for x. So we're going to do add R1, I'm sorry, that's not R1, R1. And then we're going to add R1, R1 with a decimal 1. So now we can do add R4, R1, R2. So here is where you have R4 is equal to negative x plus y. And then at this point, your R1 is negative x. Okay. And then now we're going to bring the z in. So we're going to add R4, R4 with R3, because at R4 earlier, you have negative x plus y. Now you got to add the z, because this is, now we're looking at the left equation, right? And then you're going to make it equal to 10, right? So what we can do is we can take this, subtract 10 and check for 0. That's easy, right? It's we can do it with the sign. So R4 here is negative x plus y plus z. So now what we're going to do is we are going to subtract it with 10. R4. And you can you can handle the sign like this, right? Or you can do the 2's complement of 10 and then add it. That's up to you. So R4 is equal to negative X plus Y plus Z minus 10. And since I subtracted right here, I can branch it now. So BRZ, right? We can say 0 or equal EQ. Branch to check for 10. And then for the EQ section, right? So once you branch to it, we just need to store it now. So we would say and in this one, I would use another label. So we are going to do a STI R4 to, let's say, result. Okay. And then you gotta add the fill. Or yes, fill hex. We can add it subsequent to 31003. And there you go. So this one's a little longer, right? As we need to do the branch for the comparison. So basically I moved the 10 to the left and I checked for 0. There you go. 2 options. I like the first one better because it's easy. Any question?
So we branch because we have to check if it's 0.
Yeah, because when you look at this equation, when you solve this in algebra, right? All of these value, it's going to be equal to 10, right? So in algebra, how do we check? We move the 10 onto this side, right? You subtract 10 on both sides. If I subtract 10 here, it becomes a 0, right? And then that means I got to subtract 10 on the left side as well. So it's like this. X minus Y plus Z subtract 10 is equal to 0. That's what we're doing. Because when you subtract 10 on this side, it becomes a 0. You subtract 10 on the left side, it's a negative 10 here. Yeah.
You did this for a second?
Yeah. I don't know if my key works, but oh, the classroom, the PSC. It's this one. Yep. Sorry. Question? All right. So it's, so you can do it either way. It's really how you see it, right? So if you do it that way, you gotta subtract the 10 and then you check for the 0. And in the case, if I want to output it onto the console, I just need to copy, right? Because I know that my result is in. So this should show up 0 because after you check 10, it's going to branch to this. So basically you're saying if it is equal to 0, go to EQ. And when it gets there, it's going to store it out to the result, which is, it should show 0. Okay. So now if it's not equal to 10, then we have to handle it other ways. Any questions? So I think with this one, it can go further on how we want to address it. All right, let's go forward. Just disregard all the extra stuff. So for the last one, it tells you to, I think I did, let's do this. Okay, to solve for z if x is greater than 10 and y is less than 5. And this one's a little different, but I did add some stuff here. So if we take whatever that's above, right, and what we can say is we want to solve for z if x is greater than 10 and y is less than 5. So we can break it into one piece here, that's one subtask, and then another subtask here. So we would do check conditions for x above 10. So what we can do is we can subtract 10, like what you said earlier. Yeah, no problem. Okay. So if we subtract 10 earlier, we can also branch for positive. If x is greater than 10, we're going to go to positive. Okay. So here's my code for that. I know that x is at register 1. So I'm going to put x minus y to register 1. And then once I subtract 10, right, because I wanted to check to see if it's positive. So if I have x is 11, 11 minus 10, I have a positive 1. So BRP pos here. And then at the pos section, I can store z out. Let's say that it's register 5, but we can be at register 4, whichever register. And then for the y part, if y is less than 5, then we would check the condition for y below 5. Okay, so a way that we can do that is we can subtract 5 and branch for negative. Okay, so to subtract 5, as you've seen with the x, my y is in register 2. I can take negative 5 and I add it to y and put it on register 2. Then it's going to go here to check to see if it's negative. If that's true, it's going to go to the negative. And then for the negative, I can just do NG. And I can store that out. Let's say that if we use register 5, and so if you use LDI, you got to do STI at the end. If you use LDR, you got to do STR. So I'm going to stick with STI. Okay. And then we are going to store it out to Z. And so if we use register 4, we put register 4. If we use register 5, right, we put register 5. So track your register. So I'll stick with register 4 because that's what I had earlier today. Last year when I did this, I did register 5. So any question? Okay. So now we want to display Z value on console, right? So we can store the value to register for verification. And then we want to copy to R0 for output. And then verify output at the location. So here we're just gonna do an STI R4Z like what we had earlier. And then we are going to add R4 with hex 0 and put it on register 0 so we can output, which is we do a put there. You can also do out. Any question? So just to do a C out, okay, you're gonna have 3 steps in LC3, or at least 2. Sometime more, depending on what you're trying to output. But we need to copy it to register 0 and then do an out or puts. Anytime you have in, out, get C puts, register 0 handles that. LEA also registers 0. Because if you use other register, it's gonna complain, it's gonna throw an error. Any question? Okay. So practice, right? For C, A is set at location 3330. This might be too far. Remember what we were talking about last week where we talked about 255 locations? But okay, so we'll go with the assignment. We're gonna do a dot fill 3330. For B, dot fill 3331. C, dot fill 3332. Now it tells you here that if A minus B is greater than 0, we can add 3 to R, right? R assuming that it's just a location where you can check your result. So we show a 3 there. So that means that if I operate this subtraction, I want to branch for positive. And the step would be that when we check for positive after the subtraction, then we're going to add 3 to R. So we need to fill it at another location below 3333. Okay. So let me move my code down. So we have let's put that on the bottom. Okay, so we are going to do an LDI or an LD. You could use LD. And I chose to use register 1 for A because it's easy to see as it's ABC. We don't need the C here. So load register. So here we're going to do load A to R1, right? I'll comment while you B to R2. And then what we want is we want to get that ready for subtraction. So R2, after the 2's complement, you have negative B. Right, because I have A subtract B. So I just did the subtract of B, or the negative sign B. Right, we have a sign B. And then I chose to use R4. I take A subtract B by adding them. Right, A add negative B. And then I have, because we're checking to see if this is greater than 0, then show 3. Right, less or 0. We've seen this before, so we are going to branch for positive where it is greater, negative where it's less, and 0, Z for 0. And so for the greater than, the problem tells us that we want to show the 3 at the location of R. So I need to load R to register 5 or another register. So I did that. So LTI R5 like that. And then after I load the register 5 for the R, now LC3 might not like this. You have to use like result or something like that, or C. It will not like just the R because it gets confused with register and R. So R might not be a good variable to use or a label to use there. Then once I have that loaded, then I can add 3, right, to the register that was loaded. So now if I want to display this on console, I simply copy it to register 0 and then do a put. Or at this point I can hold. And then we gotta fill all the subsequent one, right? Like A, fill. So to really complete the program, you gotta add the A and the B fill, and then, you know, this fill. Now for the second one, if we are seeing a less than value, because here we have the less, right? We're going to show a subtract 2 or a negative 2 added. So for the less, I'm only going to show you that because there's no point to repeat the first step. So when we branch for less, we're going to define the label less. It's the same as the greater than, except for we are going to add negative 2. Or you can do the 2's complement of the 2. Okay. So as we branch negative here, it's going to go to the result register after it takes A plus negative B from this register. It's going to put the result in register 4. If it is negative number, it knows that it's less than, so we're going to send it to less. And in the less, we can load it to register, or load register 5, which is our result, to the label. and then show the -2. Any question with less than? So just like how you do the if else statement, right? The best way in assembly like this is to think of it like a comparison, because it is a comparison operator. If you have a less than of a certain value, just subtract it. And if it is negative, right? Then we know it's less than. If it is positive, then we know it's greater than. If it's the same, right? If it's 0, then it is the same value. And that's how you operate comparison. So when you write it in C++, if A minus B is greater than 0, this is what's being done at the low level. Exactly. By the compiler. Okay. So if it is 0, we know that we're going to branch for 0 and send it to 0 at the label 0. You would load, right, the register 5 for R, and then you want to show the 1 at that, right? Now my question to you is, should I store here? Sure. Why should I store here? Because I load it to a register from an address, so that way I can add the 1 to it. If it shows the 1, we know that it's the same value, right? You've seen this in the lab before. And then we store it to the address so we can simulate it. And the same thing with this one. You should ST or STI it. Okay, and the other greater, same thing. Because if you don't, like we talked about before, register is not going to retain the value, right, long. So we want to put it onto an address so we can simulate it and see, oh, is it a 1? Is it a 2? Is it a 0? What is it? Is it greater than, less than, or equal? Okay. And when you simulate this, you would then put in your input value in hexadecimal at the location for A and B, right? And then you can check to see if R is. So in the case that if I use A is 4, 4 minus 6, right? I would have a less than, so I would see a 2. Any question? So the complete program looks something like this. Okay, so just a quick, because we have a little bit of time left. I load A, I load B, right? And I load R. I did this at the beginning because I know that this is where, and you can load C or whatever you like there, okay? I did the 2 complement for register 2 because that's where the B is. I have -B there. I then take that and add it with the register that has the A, which is 1. So R2 plus R1, and then put it on register 4. And then I branch P for positive, I branch N for negative, I branch Z for 0. You've seen this in the prior lab. In the positive, right, I can take hex 3 and I add it to where my R is, which is register 3. And then I store it so I could see it. Then I halt for the positive. Then for the negative, I take 2 and I add it to register 3 because that's where my result should be. And then I set up the 2's complement because the problem asks us to show -2 at the location for result. So I would then set up the 2's complement and then store it back. And then halt. And then for the 0, right, I need to show 1. So I would do a 1, add it with register 3, which is the result plus 1, and then put it on R5, and then store it back to the result location, and then halt. And in the data section, I do a fill, and then I have a data. And there you have it. We did this a few times in the prior lab. So by this point, we should be very comfortable with doing branching for comparison, branching to check value, and we will practice more on branching with loops. So with loop is you increment or decrement. And then if you decrement, you subtract until it gets to 0. Once it gets to 0, it exits your loop. That's a for loop, right? And then you can also do a do while, but or a while, then you can check to when it should exit the while, right? As we've seen in the last lab where we have a start and a restart. So as you start, you keep prompting and you can have a way to exit out of that prompt. Any question? Okay, so the whole point in this is to kind of break it down into the subtasks so you can see, right? And sometimes, you know, we have to think about how we load the label, how we're going to handle each of our operation in our equation, right? One piece at a time. Then if we're moving, you know, if we're subtracting everything and check it for 0, then we can branch it with the appropriate flags and then be able to store it out so we can check it on the simulator. Okay. So that kind of wrap up what we have to do for today. Let me stop recording. I'll stick around for some questions.